Hi everyone, welcome to the April 2DCC webinar. Our speaker today is Suji Park from the Brookhaven National Lab. And Suji, we are looking forward to your webinar, so you are good to go ahead and get started. Thanks.
Okay. Thank you for the introduction and thank you for inviting me to this interesting webinar system. Okay, so I'm Suji Park. I'm a staff scientist in Brookhaven National Lab and a Center for Functional Nanomaterials. So let me introduce our lab. Okay, so I don't know how many of you have heard of Center for Functional Nanomaterials in Brookhaven Lab. So we are a user facility, just like your institution. We are under a DOE's program. So we have all the equipment and microscope and theory support. So under the one building. So if you need something, then just please find us. We are in New York State, so it's gonna be an interesting trip. Okay, so I'm today talk about the 2D materials. You all know about the 2D materials very well, but this is my routine presentation slide, so I'm gonna start with what 2D materials are. So the most famous 2D material is the graphene, obviously. The monolayer are held by very weak van der Waals force interactions, so we can easily write it because these are very slippery. So we can consider these thin layers as multi-layer graphene. Okay. So 2D materials have been paid tremendous attention for last 2 decades. New 3D materials have found beyond graphene, and it shows very interesting properties, characteristics, because we could stack them into a new structure and find a new material properties. More interesting researches started in 2028, led by a research group at MIT. So they found this interesting twisted structure with two graphene layers by stacking them at a magic angle. By stacking them at certain angles, they can produce this moire pattern, and it actually tweaks the electric band, and they could tune the properties and generate an interesting physics like superconductor. Okay. This interesting whole story got started in 2004. These two scientists could isolate graphene by a piece of tape. And the method is very simple and handy. First, we place a bulk material on a tape and then distribute it and thin the crystals over the sticky side of the tape. And next, we position them on silicon oxide wafer and scrub it and slowly peel off. Then we start searching the usable layers and usable flakes on the silicon oxide surface. So this technique is easy and handy, and it produced the highest crystal, highest quality 2D materials with very few defect. However, this is highly manual and it is labor intensive and not very reproducible. It takes a lot of time to train people to produce the high quality, large enough, good enough 2D flakes. Of course, there are many good methods to produce 2D materials, and still the tape exfoliation is produce the highest quality. So we could use this method to make cutting edge devices or find a new structure for further applications. So to make this work easier and to make researchers' life better, we developed QPress, quantum material press, an automated 2D platform, 2D fabrication platform. We use a lot of robotics and AI capabilities, and we could use this QPress to produce and characterize 2D materials in one site. So this is the footprint of QPress. So it consists of vacuum side and the glue box side. In vacuum side, we have e-beam evaporator so that we can deposit some metals. And also we have annealer and plasma etcher. And also we have sample libraries so that we can store crystals and substrates and 2D stacks in vacuum chamber. And we also have this argon glue box, and we developed these three custom modules, exfoliator and cataloger and a stacker. So this is what is happening in the glue box. So we have a little robot and we can transfer the samples and substrates on the stage, and we start exfoliating with the robotic system. Okay, I'll explain this later. And after exfoliation is done, we could go to the microscope. This microscope has machine vision capability so that we can filter out the thin layers and do some measurements with Raman, AFM, and PL. And this is a stacker, so we could stack exfoliated flakes into a heterostructure with fully motorized stages. Okay. And also we have vacuum suitcase adapter here so that we can transfer air sensitive 2D stacks into some other characterization tools. Okay, let's talk about the exfoliation machine. So before we start, we had to think about how this type exfoliation is actually happening. To design the machine for the exfoliation, I studied a little bit, and if you look at this system, the system consists of four main layers: tape backing and PSA pressure sensitive adhesive layer, which is a sticky side, and then 2D crystals and substrate. So if you look at this system, let's assume that the backing material is starred enough. Then we have these four interfacial energies in this system. And the failure, meaning the crack, happens at the weakest interface in the system. If the cohesive strength in the PSA layer is the weakest, then it will generate this cohesive failure. If the adhesive strength is the weakest, then it will drop the 2D crystals. And if the interlayer force is the weakest, then we will see this clean cleavage. And if the adhesion between substrate and crystal is the weakest, then it will just drop it, it just pick up. So the first two scenarios, sometimes it works if somebody needs not super clean surface, but what we need is this clean cleavage in between 2D crystals. So it is hard to change this interlayer energy, and in substrate adhesion, we could increase that with some surface cleaning, but there are some limitations. So we should be able to control these two forces as well as other parameters. Actually, there is a study showing the contribution of that cohesion and adhesion, which is polymer rheology, to the exfoliation modes and results. So this group, this study simulated the exfoliation process from compression to the exfoliation. They compared two different polymer systems with different viscosity level. And they found the high viscosity with PMMA actually activate this peel mode when it exfoliates the crystals. And the low viscosity material with, for example, PDMS, activated the shear mode to, to separate the layers. And these two different exfoliation mode actually results in the exfoliation results as well. So according to the simulation result, the peel mode gets the outer layer more, and the shear mode gets the central layer. So the number of exfoliated layer is actually different. So for to control this viscoelastic properties of PSA, we need to consider two parameters. One is the frequency and the other one is the temperature. Frequency means the speed. So usually the PSA that we use in real life, they design this frequency range in humanely possible. Like, when we peel off, we cannot peel super fast or super slow, but in some certain level of the speed is designed, and the temperature range is some room temperature or some in high temperature range it below like 30, 40 degrees in general. Okay, and we the the bottom line is we need to be able to change the speed, frequency, and the temperature when we do exfoliation. Another thing we need to consider is we also peel off, right? Peel off the tape with crystal. So if you look at this Candle's equation, which is the simple equation for the peeling off process for elastic thin film. So elastic film includes not only tape, but also 2D layers as well. So if you look at this equation, it includes the Young's modulus of the material and also the peeling angle, which affects the vertical force. So if you make a large angle, which means a larger vertical force, and it makes it easier to peel off. And also the peeling speed, naturally it hardens when you peel off fast speed. So this equation tells us that we need to be able to change the angles and the peeling speed as well. And also, when it comes to the crack propagation in 2D crystal, it also important the angle crystal and the crack propagation speed as well. Okay, we designed exfoliator that can control all the parameters that I mentioned. I inspired by actually the office laminator. We designed the machine with the roller assembly. So it actually controls the rolling and peeling conditions. So for example, for rolling condition, we could change pressure, temperature, and rolling speed. And when we peel off, we control the peeling angles and peeling speed and temperature as well. So let's talk about how to actually realize this exfoliation with this roller assembly. So if you look at this manual exfoliation process, there are two exfoliation cycles. First cycle is happening between two tapes. So bulk crystal in one side and the other tape in the other side. And the second cycle is happening from tape and wafer. Okay, so basically we run these two cycles in different substrate. Okay, so this is the robotic exfoliation. First cycle, we prepare a parent tape with crystal and roll between this blue tape and the parent tape. So the first cycle is done. So this rewinder keep pulling this side up and the crystal goes this way, then it generates this peeling motion. And we change the substrate here with silicon oxide wafer and the second cycle of exfoliation with different parameter control. So this rolls and then we peel off. Okay. Okay, as you can see, we are using a 3-inch wafer. It could be just one 3-inch wafer or some diced chips on silicon wafer shaped carrier. So before we even start think about the recipe, we need to determine what PSA tape we are gonna use, right? So there are a couple of famous PSA tape that is popular for exfoliation. We tested several of them, all blue tapes and the needle tape, um, with different tack and adhesion level. And you can see, even if we use the same recipe, the residue situation is quite different. And even if we use the same PSA tape, the dicing tape, depending on the recipe, you can see different residue situation as well. So that means if you choose different PSA tape, dicing tape, and needle tape, you need to develop or adjust the recipe according to their properties. Okay, so we ended up using this dicing tape most of the time, and we're targeting the minimum residue and the maximum yield kind of situation. Okay, so to develop a recipe, we played with some parameters. So this is one of the example that we actually changes during the recipe development. This is an example when I tested that residue situation. And we could successfully develop some go-to recipes for the HBN and some TMDs and graphene as well. If you look at this chart, and depending on the peeling conditions, in particular speed and angle, you could actually improve the yield significantly with the robotic system. But this is very one-dimensional metric because every time you use different size crystal and different size substrate, so it is not super reliable method to evaluate the exfoliation result. So for further optimization and a better understanding of the exfoliation mechanism, we developed a statistical approach to more effectively evaluate the exfoliation efficiency. For example, in this regime map, we actually count all the flakes and fit normal distribution. And then this regime map shows the frequency of the usable means large enough and fat enough, not super thin so that they kind of needle-like, which is not usable. And this axis shows the expectations, the reproducibility, and the radius shows how strong this tendency shows. So this chart is our metric to optimize the exfoliation recipe and also the study each parameters. And we try to increase both metrics by tuning the recipes. Okay, the quality of the exfoliated flakes has been proven by our users. So we have a lot of users. We support users through user proposal, and user can use QPress in person, or we could send around exfoliated sample if it is not super air sensitive, or we support them through the Zoom, depending on the proposed work. Many users combine their visit with synchrotron as well, so that is another benefit for us. Okay, well, so that was the exfoliation, and we need to find the flakes a little better way. Okay, so we have this cataloger based on the optical images. So for exfoliated flakes, we use optical contrast and color to estimate the thickness and lateral size and shape. For thin layers, this is optical image and this is AFM image. So sometimes the optical image shows much better contrast, so that we can easily estimate the thickness and by just contrast. Or some material like HBN, it displays different colors, so it is very useful way to estimate the thickness. The thickness of the contrast and color of the flakes are highly depending on the silicon oxide layer. So the oxide layer thickness shows this is the 90 nanometer and this is 300 nanometer silicon oxide. As you can see, you see different color and contrast. So sometimes specific material shows better on certain thickness of oxide. And sometimes the different color channels shows better contrast on a certain materials. So all this information is very useful to develop AI capability to identify the crystals and classify the thickness. The early attempt, they used unsupervised machine learning. So they showed a lot of images and let AI model find the features and make a cluster. And basically, this cluster shows a certain conditioned flakes. However, the accuracy was not super good. So now, the later people use deep neural network, training data set with already known reference data, and the accuracy is slightly better, but it requires a lot of data set to train. So for like very common materials like graphene or other TMDs, it may work, but some exotic materials are very hard to find this enough training data. So recent attempt is they basically produce the synthetic data set to train the model and then increase the yield, the accuracy with very few images, the very few real images. However, still the problem is it every time we take images, it changes the color or contrast slightly because the background, in particular, the silicon oxide wafer thickness is not super uniform, even if we buy the wafers from the vendor. So the color, the background color, it changes. And also people use different cameras, different lighting conditions, it slightly changes image quality. So then it actually causes a lot of problem for us as a user facility, and we are dealing with various materials and various substrate. So early on, we developed this deep neural network model to find this graphene. So it finds this graphene, thin layer graphene out of very large area, which is like 5 by 5 centimeter. However, the limitation was we frequently encounter new 2D materials and new various substrate conditions. So we tweak a little bit of approach. So we started using more human input. So we find all the flake and then filter out based on their colors. Then we can it's kind of filter, a little better filter, so that we can easily just check the result immediately without training data set. However, it still needs human input and still it assumes that the background color is uniform across the data set, which is not always true. So we try to combine this ML and this heuristic approach together, so to overcome these limitations as well. So the QPress cataloger has not only machine vision capability, but also we have some basic characterization functions like Raman, AFM, and PL measurement to verify the crystal quality and measure the thickness if we do not know the optical contrast of the material. Okay, so finally, we are ready to make 2D heterostructures. Okay. Okay, we visited this system for exfoliation, but when we picked this one, the best conditions for exfoliation. But the other three are actually the mechanism for the transfer. So we use dry transfer, hot and dry transfer, which means we use sticky polymer to pick up the top layer and then change the bottom, the next layer, and the top layer will pick up the next layer, and we repeat this process. So basically, we play with this temperature and very accurate motion control between the stamp and the sample. When it comes to stacking, as I briefly said, the important thing is the precise alignment of these crystals. And also we have this twistronics blooming, right? So we need to be able to change the angles and the positions to maximize the overlap and maximize the yield of the usable area. And also we want to make the interface clean. So we don't want to drop each layers like instantly so that we can easily trap these bubbles, or if there are some tape residues or other not welcoming materials in between, we want to clean it out when we make the stack. And also, we don't want to generate the wrinkles or defects by just giving like shock in terms of when we change the temperatures as well. So we designed this motorized stacker with 6-axis motion control and precise temperature control on substrate and also the polymer stamp. So this is the okay. Okay. Okay, so we have 3-axis control on the substrate for scanning and making angle, and 6-axis motion control on the stamp so that we can fix the pivot point and roll or slowly, gradually make a contact on the surface. And also, also we make this temperature controller for stamp sticky polymer. So if we do not have this capability, then it is easy to make these wrinkles between, when we pick up the flake, then the polymer will contact on the hot surface. But after picking up, it expose the just room temperature and then it drops the temperature. Then it is easy to make this kind of wrinkle. And actually during the stacking process, it repeats expand and shrink process. So we decided to add one more heater on this stamp so that we can maintain the temperature so that we can reduce the thermal shock during the stacking process. Okay, this one is one of the example of early user experiment. So this one is the planing process. So we are laminating the top contaminated graphene on top of HBN, and we controls this the temperature and the stamp motion so that we can push this contamination out from the interface, and we could generate a very clean area, which it was the largest area that we could generate, reported in 2022. Okay, I don't know the current situation, but this finding was, this technique was very useful to make a clean area if we are using already contaminated polymer flakes. Okay, so for summary, I introduced the custom-built modules in QPress. Then, okay, so then where are we now? Because there are many definition of automation and autonomous experiment in generally used, but I think we are currently at here. So we've developed each capabilities, but we are working on connecting them with little robots and make a smooth process. And once we close this loop, then we could optimize the recipe more easier and make a stack more autonomous way. And we're pursuing this direction in the future. And we introduce more and more AI capability to control parameters and the process. So I hope that we could complete this autonomous fabrication in 2D heterostructure fabrication field. Okay, so this is our team, and I'm very grateful for our collaborators, early collaborators, who helped us to develop these machines and taught me how to stack and exfoliate. Okay. Any questions? I'm ready to get questions.
Any questions online or in the room?
I have a question.
Sure.
So you mentioned that you try to avoid having any wrinkled films because ideally you usually don't want that, but has there been any interest in creating controllably wrinkled films during the
Yeah, of
deposition
course.
process?
Yeah, of course. Everything that you can control, right, could be engineered, right? But in our approach, the wrinkle is one of the enemies, so we want to avoid the wrinkles. But as you said, I showed the examples. So far, we don't have any users who wanted to make um, the wrinkles on purpose, but the figures that I showed, this one, all right, oh, it doesn't move. Okay. Okay. This one. So this is the paper that people actually intentionally make this wrinkles and strains in a kind of controllable way.
Mhm. Thank you.
Any other questions?
I guess I can ask one. What are you doing to try to align the crystal lattices when you're, purposely trying to twist layers with respect to each other?
Okay, so to make twisted structure, there are two approaches. So one is you exfoliate large area, one giant flake, and then you pick up the one side and then move it over the other side and twist and pick that up. Okay, that is more like the general way. But another way is you exfoliate two separate flakes, and because of the crystal structure, it usually have like very sharp edge. So you predict the angle. And then it actually, for example, if it is like TMDs is triangle shape, right? So the chances are actually 50-50 if you're relying on one edge, because people sometimes twist different flakes, different kinds of flakes, so to make a hetero twisted structure. Then that is one of the way that people do. And we have a plan to make some other functionality station, for example, like SHG or some other way of finding crystal orientations more easily. That's the plan.
Yeah. And when you're looking for, layers of a particular thickness, if the optical techniques are kind of difficult to say with certainty that you know what you're looking
Right.
at, how far away is, like high-speed AFM from being able to search large enough areas to be useful to you?
High speed AFM. I'm not super familiar with that.
So there are some AFMs will allow you to scan,
How
at
fast?
microns per second types of
Okay.
speeds, which is still pretty small, but I don't know what the state of the art is for how fast you can possibly scan.
Yeah, there are several candidates that we are currently considering, like, the conductive AFM and some PFM, HHG, and other techniques. And the polarized Raman also can find some crystal, but not one characterization tools can cover all different 2D crystal, except if we can add electron scattering stuff, then it may be. But it's technically it's kind of challenging to add it to it.
Yeah, especially in a glove box. Yeah.
Anything else? Oh, go ahead, Daniel, if you want to unmute.
Yeah, so I guess I just had a sort of quick question. You hinted that you had done some statistical analysis in terms of the exfoliation process with a variety of degrees of freedom, with the robotic control and temperature. I mean, was there any sort of insight between angle and time and temperature that you pulled out within that parameter space that was like,
Yeah.
oh, we can recommend this to the entire community, and this is maybe how it
Entire
should be
community.
done?
Okay. I
Yeah, like,
haven't
yeah.
added here, but maybe I don't have the slide deck here. We found the huge impact with controlling the peeling speed. So if you go very slow peeling, it usually generate thinner and larger flakes. And also you could kind of limit in our system, it's a tape to tape exfoliation, but in the manual system, it could be just like, repeating this folding unfolding process, because this process actually breaks the crystal, the initial crystal. So if you in our system, if we go like more than 2-3 times of this tape to tape exfoliation, it reduces the yield that the resin side, it goes like very close to the origin. So that is one of the insight that we could provide. We're trying to test the different parameters, but as I said, it's a lot of parameters that we could control. So we are trying to make them, the optimized, machine learning based, the Bayesian optimization or other optimization techniques to optimize the recipe.
Okay, thanks.
I have one more question.
Go for it.
Have you guys worked with very delicate target substrates? I ask because I'm in the middle of trying to develop a procedure to do HBN, TMD, HBN on a TEM grid, which requires a lot of finesse, and it would be great if that kind of a procedure could be automated.
Yeah, we tried to transfer on the TM grid as well, but there are different types of TM grids, right? The copper mesh or silicon nitride. So in our experience, if you just use membrane, silicon nitride membrane, it's not super bad. The yield is not super bad, but you need to be more strategic because if you place it on the center of the membrane, it will break it. But if you go a slightly the side with more supporting area, then it will survive. But the copper mesh, yeah, we didn't, yeah, I don't have any successful story with that.
Okay, that's what I'm working with. So thank you.
I'm sorry about that. But probably you could I think that the problem was the contact area was super small. So you could not just drop it kind of nice way. But if you reduce I don't know if you can make the mesh more, with like thicker lines, for example, then
Yeah.
yeah, probably.
Okay, thank you.
But there are a couple of other stamp material. So because if it is suspended structure, then if you use the polymer that requires a melting and cleaning, that it may affect a little bit. But there are other polymers that does not require this cleaning process. It just drop it nicely. But I cannot guarantee that is super clean though.
Okay, we use polycarbonate, and that's been
Yeah,
okay.
that is the most common. There are a couple of papers that use the PVC.
Okay.
They did not require the cleaning.
Okay. Keep that in mind. Thank you.
Awesome. Thank you, Suji, and thank you, everyone. We'll see you on Tuesday, May 5th for the last webinar of the semester. And thanks again.
Thank you.